now, so we'll be doing the last section, 1111, Taylor polynomials. I'll also connect 1110, which is Taylor series. It's the same stuff as we're doing this. Actually do Taylor polynomial, jump back to the Taylor series. I mean, to make the Taylor polynomial, to make the Taylor polynomial, we need Taylor series. We need the Taylor series. And we'll wrap this stuff up. So the first problem we'll start with asks us to find the Taylor polynomial. And you'll see that subscript is a 3, piece of 3 of x for the function. And since we did trig functions last time and the exponential functions, I thought this time we'd do natural log. So I chose natural log of x. And it's centered at a equals 3. So the first thing is you'll notice when we were doing these last sections, just yesterday when we were doing the Taylor series, when we wrote it all out, you all noticed they were polynomials, right? They were always polynomials, and that's why they call these also Taylor polynomials, functions that are written as polynomials as you head towards infinity. All those terms just keep adding up. X minus 2 to the third, x minus 2 to the fifth, etc. But this subscript of 3, I want to be clear about that. What does that mean? Just 3 terms? No, that means degree 3. So would you put that in your notes or just remember that? When they write this T sub 3, they're talking about degree 3 polynomial. A polynomial of the 3rd degree, which means something like this. The highest power is x cubed. Now it might say x minus 5 cubed, but the highest power will be a cube. That's what they're asking. That's where they want you to stop. So the biggest mistake sometimes, especially when students used to pull out like the TI inspired 89, they would think, oh, I'll put it, it would only end up the, we do the first 3 terms, but we put them in at x squared. So that's what that means, degree of 3. Well, to do this, we bust out the Taylor series. We need the nth derivative evaluated at a, and this is centered at what, 3? So we'll do the nth derivative at 3, x minus 3 to the n factorial. And so I'll start writing this thing out. Like, all right, what's this function going to be equal to? This function here will be equal to the first term. I would like to do this. I'm going to put a box. I'll explain my reason behind this. X minus, where's it centered? 3? 3 to the 0. Now I'm just going to keep writing. I'm going to put a box. X minus 3 to the first. Box. X minus 3 squared over 2 factorial. Plus box. X minus 3 cubed to the third factorial. Aha, and there's that degree of 3. So we won't have to go any further. I'm just going to go. There's that 3rd degree. The reason I write it like this, I was doing this last section, I want you to realize that all these polynomials look the same. They always, no matter what the function is, it's these boxes that we got to figure out that involves doing this nth derivative of that. So it doesn't look confusing. It's like all these polynomials will look like this. Unless it's centered at 0, okay, you got x minus 0, x minus 0, x minus 0. But the denominator is always going to do what? 0 factorial, 1 factorial, 2 factorial, 3 factorial. 3 factorial is just 6, right? Make sure that dot's under 2. 2 factorial is 2 times 1. There's 2, 1 factorial is 1, 0 factorial. But that's why I write this. So it always comes down to what am I going to put in these boxes? And it's helpful if we just make a table. And we'll do that now. We can go off to the side and make a table here. First column, we just use n. Second column, how about the nth derivative of x? And then the third column, we'll actually substitute the a value, which in this case was a 3, right? And we're going to figure out, in this right column right here, all the box values. So that's why I do this. So it doesn't look like it's something crazy. You know what Taylor polynomials look like, Taylor series look like. They all look like this. It just depends on these coefficients. And we know generally sometimes you get zeros for the coefficients. Wipes the thing out, right? Makes it flip-flop like every even or every odd. We'll see that again today. All right, so do I start at 0 or 1?
0, 2.
You understand that? Start at 0. 1. We don't have to go to 3 here, right? You said 3 to 3. We got here. Okay. Keep in mind here, we're not doing a derivative, we're just putting the original function in. The actual original function, which is just what? Natural log of x. All right, substitute 3. Remember, that's an irrational number, so let's just leave it natural log 3. Right? And natural log of e is 1, but natural log of 3 is just irrational. We just leave it like that, right? Okay. What's the derivative of natural log of x? 1 over x. 1 over x. I'm going to write it this way, just because it might help you do the next view. And then put an equal sign 1 over x. I just want to write it 2 different ways. Because we know we're about to do the derivative of x to the negative 1. It might help you with that. Hey, so what's this number? 1 over 3. You got it. All right, so what's the derivative of that? I wrote it like this, so you might find it easier to do the power rule. So that's why I wrote it 2 different ways. So we're like, oh, we're going to have to differentiate that. I didn't want you to think you had to do quotient rule. You don't have to do quotient rule. We can just do power rule. What's the derivative?
X to the
Negative 1. X to the negative 1? Negative 1. X to the negative 2. Now write that the other way. That's negative 1 over
X squared.
x squared. Okay. So I just thought I'd write it 2 different ways. Plug in a 3, what do you get? All right, we only have to do one more. What's the derivative of negative 1 x to the negative 2? Is it negative?
2 x plus 2.
Yeah, because a negative times a negative is a positive. So positive 2 x to the negative 3. And then, okay, 2 over x cubed. Everyone okay how I'm moving these back to the denominator, these exponents? Yeah. Hey, what's that number? 2 over 27. Okay. Where do these numbers go? That goes there. That goes there. That goes there. That goes there. This time, though, we don't have to write our solution in sigma notation. You're probably going to find this problem a lot easier than yesterday. We're going to write it as a polynomial. They said find the Taylor polynomial of 3rd degree. And we'll be done. But we will clean it up. Like, what is 3 factorial again? 6. So we'll write it nicely. Like it looks like an actual polynomial from a college algebra class. Right? We'll actually write it that way. But we won't put it back into like yesterday. We put it back to a power series. We found the radius of convergence and all that stuff. So when I'm going to put these numbers in here, this is a 1/3. This is negative 1/9. This is, oh, thank you. I'm going one off. I got my arrow right there. Thank you. This is natural log of 3. This is, yeah, I was going to get to the end and say, I've got nothing for this. Negative 1/9 and 2 over 27. Okay. I'll get this line out of the way. We're just not going to leave the answer like this. Now, I have an equal sign here. I wanted to wait till the end and go, what am I saying this is equal to? I mean, you could call it f of x, but it's not really that function, is it? We're talking Taylor polynomials, it's an approximation. It would have to go towards infinity. So we just call it t sub 3 of x. That's what we're calling the Taylor polynomial. You can't write it as f of x? Well, we have to go all the way and put the dot, 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 dot. This just said find the Taylor polynomial for the function with the 3rd degree. So I'm going to write this and just write all this out. So what's 0 factorial? Excellent. 0 factorial is 1. X minus 3 to the 0 power. What's that? X minus 3 to the 0 power is 1. Do you all agree? So this entire expression isn't 0. It's just a natural log of 3. Was that all right with that? Yeah, good. All right, plus 1 factorial is 1, right? Go like that. I don't have to put the power of 1. Just cleaning it up, right? Notice this is minus, so I'm going to put a negative or subtraction sign. I can put that 9 with the 2 factorial, can't I? 2 factorial is 2. What's 2 times a 9? 18. Can you help me with this? 3 factorial is 6. What's 6 times a 27? What's 27 times 6? Is that 162? So I'm going to put, for this one, 2 plus, I've got a fraction of 2 over 262, and then I'll have the x minus 3 cubed, right? Can I reduce that though? And this is that, I'm talking about that number right there. It's got a 2, it's got a 27, and it's divided by 3 factorial. I'm saying, I'm just simplifying it. You're like, well, that's 2 over 27, I'll put an equal sign, over a 6, which is 2 over 27 times a 6 that's sitting right next to the denominator, because it's times 1/6, which is 2 over the 162. But I can simplify that, can't I? What is that? 1 over? What's half of 162?
81.
81. It's all right. Of course, you can do the frac button. If you don't like doing this stuff. You know, just do 2 divide 27, then divide a 6. Frack it. Get that one out of the way. Done and fair with your answer. This is it. We stop right here. That's the Taylor polynomial, third degree. But you'll notice it's a polynomial. Good idea. One of the main reasons behind this section, why they do this now, is so that with the series, sometimes we get lost with the fact that these are polynomials. That's why we do this.
If that was like t sub 4x, would you go to the fourth then?
That's right. You go to the fourth degree. And the biggest error I ever encountered, Isaac, is students just accidentally see this. They think that means only, oh, I see 3, so I guess I only do 3 terms.
Okay.
And they always cut it off one short. That was the only problem. Do you have it? I know you got an 84. Does anybody in here have an 89? Okay. Do you know they do Taylor polynomials? And it's like you could type in, or you put a comma, and it leaves you a spot to put the 3 and stuff like that. Put the degree.
That's cool.
But still with them, sometimes students will miss that first term. Can you write this in reverse if you wanted to? Remember we always taught in algebra, let's go from the highest degree down. You can, but you can leave it like this. So you probably find this easier than yesterday, because after this yesterday, we did 2 things. Number 1, we wrote it back as in sigma notation. That took a little while, get it all fixed up. And then secondly, we had to find the radius of convergence. This one didn't ask us to do this, that's all we had to find. So on that note, I'd like to return to actually writing some as a Taylor series. I'd like to do a Maclaurin series. So I'm using that word Maclaurin series. That's going to be our next problem. Maclaurin series. What's the A value?
0.
0. So it's like we don't need a new formula. I'll just make that a 0 and that a 0. And x minus 0 just becomes x, and x squared, and x cubed and stuff, right? So we'll do that next. We'll work out a problem, we'll figure out the actual series, and then we'll come back and we'll do a problem from section 1111. So to be honest, this problem we're doing now, it's actually a problem from 1110. We're going to figure out a Maclaurin series for a certain function. I want to give you something where you had to use like chain rule. We did it yesterday. Remember, what did we have? E to a 2x or something, or E to a 4x?
Yeah, it is 4x.
Yeah, it was E to a 4x. We kept going 4e to 4x, 4 squared. So we'll do one of those again with the chain rule. So, hey, super job. Any questions on this problem? And the reason I use that because the problems in textbook for practice, they actually do 33. Like I get 7, could have done 43. Kept going. The more terms we do, the more what?
Accurate.
The more accurate it is, the closer it is. So if you want to play around with the technology and start graphing these, right? What's the natural log of x graph look like? Just kind of what? Goes like that. So the more and more terms you keep adding into your calculator, it should get closer and closer in terms of that approximation. Cool. Like this problem. I'll wipe this out, but we're going to make another table. I guess I can leave this. I should go like this. Let's see how far we go. Maybe we'll go up to 5 this time. Find the Maclaurin series. For the function f of x equal to sine of pi x. So this time, everyone, we will write it in sigma notation. Because they want to, they want the series. But the first thing we do is we're going to write out the polynomial, aren't we? Yesterday we did a sine, didn't we? I think I centered it at pi over 2. Is that right? So you might think, well, do cosine this time. The reason I chose sine, I wanted you to see that yesterday we centered it at a equal to pi over 2. This is a Maclaurin series, so where is this going to be centered? 0. So you'll notice the powers here, I think we used 2n. Yesterday we had like 2n, everything to a 2n. It's going to be different. So I don't want you to think, after doing that problem, that you assume, I guess it's always 2n. The power to the 2n power, or 2n factorial when it's sine. So this is the Maclaurin series for the function f of x equals sine of pi over x. We still use this. We'll just center it at a equal to 0. That's what that means. This means center it at a equal to 0. All right. Well, the first thing I'm going to do is start writing everything out. All right, what do we got? Equals. You don't have to do this. You know my reason for doing this. Is so you recognize that every daggone Taylor series, Maclaurin series look the same, right? I'm doing it again with boxes, and we'll get these numbers, we'll fill in the boxes. Hey, but before I keep going further, can I rewrite this a little bit more simpler? X minus 0 is just what? X. So I'm going to do that. And this x minus 0, I mean, it would be silly if I keep writing that, right? So I'll just write x to the 0. X to the 1. That's what I'm going to do. I'm going to come back. At least with the Maclaurin series, I can just x to the 0, 0 factorial. X to the 1. X minus what? 0. X squared. Last problem we went out the Q. Let's go up to the 5th. Still got enough room here. X to the 5th. Here, I'll put right here. Plus dot, dot, dot. So in our table, let's go out a little. All right. My favorite is this is just going to be 0. Actually, after we do this whole problem, we compare it to something, we'll come back to section 1111. We use it to work one of the problems in that section. Okay, let's get this thing rolling over, and we're gonna have to do derivatives of sine of 5x. Here with the 0, I just write the original function, right? Sine 5x. What's sine of 0? Sine of pi times 0 is 0. Sine of 0 is 0. Aha, first term is 0. That first coefficient, that's going to be a 0. Actually wiping this out. Another thing I want you to experience, you go, wow, does that affect it somehow? We'll see. What's that derivative? I actually write this out, SCS. We're going that way, right? Derivatives. So it's going to be positive cosine. What do y'all think?
Pi.
Thank you. That's wrong, right? I'm forgetting the pi, the chain, pi, cosine, pi x. All right, plug in a 0.
Pi.
Well, pi times 0 is 0. You get the cosine of 0, you get 1, and you get a pi times a 1. So is this just pi? Everyone all right with that? I know, it's weird. You think, wait, it's not negative pi? No, because you got the cosine of 0. Great thing about plugging in zeros. What's that derivative?
Negative.
Negative.
Pi sine pi x.
Pi, and then you got a sine pi x, and then I got a chain rule, multiply the pi to the pi, get the pi what? Pi squared. Now plug in 0, what do you get?
0.
Sine of 0 is 0. So we notice this is going to be one of those alternating series. Cosine is similar. Cosine is similar when you deal with sine and cosine. All right. Now we can speed this up. Some of you probably already blasted this thing out. You're so quick. Let's do a negative sine, or negative cosine. So we got negative pi. What will that be? Cubed? I see the pattern now. What will the next one be? I'm going to keep rolling. What's the next one? Pi to the 4th? Cosine pi of x. Okay, I can see that's a 4. And finally, the derivative of cosine is a negative sign. I come back to another negative pi to the 5th. Is cosine of pi x. Yeah, the derivative of cosine right there will be
Sine.
sine. So we got SCS. That's negative. The derivative of the negative sign is negative cosine. But the derivative of that negative cosine right there turns this into what?
Sine.
SIN.
So
There's a full circle.
this last one's positive, not negative.
And then the last one will be positive. All right, plug in those zeros. What's this going to be?
Negative pi cubed.
Negative pi cubed times cosine of 0 is?
Negative pi cubed.
Negative pi cubed. I just want to stop there for a second. Does everyone agree? Cool. What's sine of 0?
0.
0 times pi to the 4th is? What happens here? All right. Well, let's go jam these in here. Where's that going? Whoop. Boom. That one. Next one. The next one. And this is a 0. And then this last one is positive. But in this problem, you and I will go back and write this as a Taylor series. You probably could have figured out the pattern right after here. The big thing is the ones that had zeros. Which one had zeros? This one? You're gone, right? That's going to be gone. And that's gone. So this is where I encourage you to write this again. And this is where we're going to focus our eyes. Get our eyes on this.